Hello class, Mr. Ullman here. I wanted to share with you a little bit on carbon cycle and greenhouse effect. Now at this point you certainly have read quite a bit, and you probably have a decent amount of prior knowledge on both of these subjects because it's something that you certainly would have heard about before, and you've already done some reading in your textbook on it. However, I just wanted to provide you again with as many opportunities and resources as possible to make sure that this is something that you know, and you know really well. For that reason, I'm actually borrowing here a presentation from another biology teacher. This is from i-biology.net, and I'll be using these slides to be able to guide you through a couple of things here. So first of all, for carbon cycle, you should be aware where does the carbon dioxide in the atmosphere, where does that come from? What is the sink, or what is the place in the world where carbon dioxide can be stored for long periods of time, and what processes return carbon back into the lithosphere, or the actual rock part of the Earth. You know the carbon cycle pretty well if you can answer those three questions. So if you want to pause it, maybe consider that, and then when you hit play again, I'll reveal those answers for you. So when we look at carbon dioxide, respiration is putting carbon dioxide into the air. Respiration from animals, plants, bacteria, all living things are putting CO2 into the air. Decomposition, as things break down, through that process of bacteria and other decomposers breaking down dead and decaying organic matter, no matter where it came from, adds more CO2 to the air. Diffusion of carbon dioxide from the water, from the oceans. Burning of fossil fuels, or any type of combustion, is going to release more CO2 into the air. Photosynthesis will capture the CO2 out of the air, and it will store that CO2 in many different forms within those plants. There is a little bit of diffusion into the oceans, and that's one thing I'll come back to in a couple of minutes. The processes that return carbon to the lithosphere are the decomposition of organic matter when it gets buried and then trapped within rock. So, examples could include the carbon that is stored up underground in the form of oil, in the form of different types of shale rocks, in the form of coal. All of those are ways in which carbon has been stored underground in the lithosphere. Also carbonates, so the limestone that is produced by corals would be a great example of a biological way to turn carbon that is dissolved in the water into a type of rock that will then keep that carbon stored away for theoretically forever. So looking at carbon cycle, you should be able to label each of these different aspects of the cycle. So again, if you want to pause and see, A, B, C, D, E, F, if you can figure out what those are, and then when you hit start, you can see the answers. Okay, taking a look. You're certainly looking here now at the greenhouse effect. So a couple of dotted lines here, looking at the first dotted line representing the troposphere. That's the upper layers of the atmosphere where most of these greenhouse gases are doing their work. And then beyond that, at the much higher level of the atmosphere, is the ozone layer. Now the ozone layer is absorbing some of the ultraviolet light, but the ozone layer lets all of the light in the visible spectrum to pass through and to hit the Earth. Some of that is going to be used up. That energy is going to be used by plants, but remember that those wavelengths towards the center of the visible spectrum, in the oranges and yellows and greens in particular, are not used by plants. A lot of that energy is bouncing back off the surface of the Earth, radiating out into space. The greenhouse gases are trapping some of those wavelengths of light and then re-emitting those back into the Earth, thus warming the Earth up. So here, looking at those layers of the atmosphere, so the troposphere is the very lowest, the lowest layer of the atmosphere, and the greenhouse gases tend to be towards the outside of that troposphere. So still several miles out And as you look even further, stratosphere, mesosphere, thermosphere, each of those layers has increasingly lower concentrations of gases, and the less gas there is, the less likely it is that there's going to be absorption of energy in the form of those wavelengths of light. Greenhouse gases you should know, and one final note here, looking at the difference between some of the different planets. Mars has a much thinner atmosphere, and thus it has the greenhouse effect on Mars is much lower, and so the average temperatures there are well below freezing. So again, not very hospitable to life. Venus has a very thick atmosphere. It's heavy with a lot of CO2. The majority of that atmosphere is CO2, and so the temperatures on Venus are hotter than any place in the solar system, even hotter than the surface temperatures of Mercury, because even though Venus is a little bit further away from the sun, the atmosphere traps so much heat that creates temperatures in excess of 400 degrees Celsius. So Earth is right there in between. A small amount of CO2 in our atmosphere provides enough heat trapping to raise our temperature up above freezing, which again is optimal for life. When we look at levels of greenhouse gases, correlation, so again there's a difference between correlation and causation. So again we're talking here about a correlation, two things that are happening simultaneously, a rise in CO2 and a rise in temperature. So you can see the red line showing the temperature data, and the green line blue line are showing amounts of CO2 in the air. CO2 measured on the vertical axis on the left, global temperatures on the right. So you can see the temperature difference, is not a huge amount. So you can see in degrees Celsius from the bottom up to the top is just a little bit over 1 degree, which would be a little bit more like 2.2 degrees Fahrenheit. So not a huge difference in terms of the number of degrees difference, but that is actually significant enough to have a pretty big impact. So the question becomes, if there's this correlation between those two things, how do we know that one thing is really causing the other? And so that's something that takes a little bit more work to be able to do, to show that there is this connection between the CO2 that we are producing and that rise in temperature. And that's what there is a little bit of debate about, not much, but there's a little bit of debate. So some of the evidence in terms of those measurements that you just saw in terms of CO2 and measurements that you've seen in your textbook. Again, we've talked about the rising and lowering seasonally of each of those of the carbon dioxide year after year. This goes back to a man named Charles Keeling who was working at the Mauna Loa Observatory in Hawaii, and the curve that you see here is known as the Keeling Curve, and it's become a pretty important piece of data that has been used as evidence to show that not only that the climate is changing, but the fact that CO2 is correlated with that. Now, this data has been going on since the late 1950s. Charles Keeling and then his students and successors who have worked there in the years that have passed since. But we can look back and we can see the carbon dioxide levels in the much more distant past. And that's because when snow falls in places like Greenland and in Antarctica, as the snow falls, that snow will trap little bubbles of air. And those little bubbles of air will contain a representative sample of the mixture of gases that are on the Earth at a given point in time. So we can now go and we can drill into the ice in places where the ice never melts, like Greenland and Antarctica, pull up what are called ice cores. So as you can see in the picture here, very long, very thin tubes of ice. And those tubes of ice will contain all the way through all the different layers, will contain those bubbles, and those bubbles can be extracted and analyzed using some sophisticated pieces of chemistry equipment to be able to see exactly what is the percentage of all the different types of gases. And so measurements are taken to see how much CO2 are in those cores in that ice looking back into the past. The last thing I wanted to take a look at in this podcast was a look at atmospheric CO2 measurements in a database called CDIAC, and this is a governmental organization that runs all of these stations that are collecting this data on carbon dioxide. And so to take a look there. Alright, so this is the CDIAC, Carbon Dioxide Information Analysis Center, and it contains a wealth of really, really helpful information about everything carbon dioxide related. All kinds of data collected from all kinds of places. There's interesting graphics, things like you see here, where there's this 3D representation of a global map, and to see what parts of the world are responsible for producing different amounts of carbon dioxide. So you can see, United States versus Western Europe versus Eastern Asia, and you can see how amounts of CO2 that have been created correspond to all the different population centers on Earth. And so you can see Japan and South Korea and China versus much of Northern Europe, England, and then here to the United States. And really those peaks really correspond to places where all the major cities are. Now, one of the things I wanted to look at was to see how we can use this as a way to be able to find sometimes more local data or more specific data for things that we want to look at. So I'm looking at data, fossil fuel CO2 emissions, and I'm coming down to the state level. You can see here monthly CO2 emissions from fossil fuel burning from different sources: total fossil fuels, solids, liquids, gas fuel sources. So if you look at, for example, a gas fuel source, this is methane, and you can see how month by month the amount of methane being released into the air is shifting. And so you can see here December, January, February, that's the peak, because that's the time when people in America are running their furnaces and burning a lot of methane, because that natural gas produces a lot of our heat across the country. And so in June, July, and August, when you see all those valleys, those are corresponding to times when people are not using their furnaces, and so the amount of CO2 being released into the air is a lot less. So there is not just a seasonal difference in terms of photosynthesis and its impact on fossil fuel production, on carbon dioxide production, but there's also a big difference based on the habits of humans. Now, I wanted to look at the state level here and take a look at Illinois, just as an example, and we can see fossil fuel emissions from 1960 going up to 2010. This is total CO2 emissions just from fuel burning, not total CO2, but just from fuel. So coal, oil, natural gas. Now, as we look, the biggest difference happens right here in the late 70s into the early 80s. Otherwise, CO2 is fairly stable to slowly rising, and it matches pretty closely since the early 80s with the population here in Illinois. As population rises, you have more people using more products that burn fuel, and so you expect CO2 to go up. Now, this big decrease, though, there weren't a lot of people leaving Illinois at this time. The population was pretty stable, but the amount of CO2 went down, and we can see that it had to do with primarily the liquid component. So that liquid component is gasoline. Now, gasoline is primarily used in cars, trucks, and different whatever other transportation devices. And the reason we had this decrease was because of government regulation, because in the late 70s, the federal government enacted new standards that required cars to be more efficient. And in being more efficient, they were then going to burn less gasoline to be able to get a family further for less fuel. So in doing so, even though the car companies fought against it, they were not in favor of having to redesign their automobiles, but the end result was that we had more efficient cars. It saved people money because they didn't have to buy as much gas, and less CO2 was being released into the atmosphere. So it was certainly a win for the environment and a win for individuals. It put a little bit of stress on those companies, but they came through okay. And that's a pretty good example to see how it is that we can both look and see and be able to interpret data, and then also to see how the role of the government in being able to enact laws related to environmental issues can be successful and can end up having a pretty big impact on CO2 levels or whatever other environmental issue is being considered. So we will look a little more at the effect of CO2 on the atmosphere in our next podcast.